Hello everybody, welcome into another lesson. So today we are starting the matrices unit. Now, these are ultimately going to be tools we can use to also solve systems of equations, but for this lesson and the next lesson we're not going to do that. Today's lesson is just going to be an introduction to matrices and what they are, and a little bit of addition and subtraction with them and scalar multiplication with them. Next lesson we'll do matrix multiplication. So here you have what's called a matrix. That's the singular form. The plural form of matrix is matrices. You talk about matrices if you're talking about more than one. Well, what is a matrix exactly? A matrix is a rectangular array of numbers that is classified by the number of rows and the number of columns that it has. So let's take this matrix here with entries 6, 2, -1, -2, 0, and 5. So this here is a matrix. It's a rectangular array of numbers. First, you always classify it by the number of rows it has. People often misclassify them because they get rows and columns mixed up. Rows are going from left to right. So the number of entries you have going from left to right is 2. You have 2 rows, the first row and the second row. Then the columns go from top to bottom. So you have 1, 2, 3 columns. So you got 2 rows, 3 columns. This would be considered a 2 by 3 matrix. That's how you classify them dimensionally. 2 rows by 3 columns. That's a 2 by 3 matrix. Now, there are special types of matrices. There's one other that's not listed here that we're not going to talk about in this lesson called the identity matrix. We'll talk about that when we use to solve systems of equations, but for now, all you really need to know are these 4. You have what's called a row matrix if the matrix is just one single row. You have just simply one single row. That's all it is. You call it a row matrix. Now you have this matrix 3, -2, 0, 4. Let's classify this matrix. So it's obvious there's one row, right? So it's a 1 by what? How many columns are there? You got 1, 2, 3, 4 columns. So this would be a 1 by 4 matrix. Now, just like a row matrix, there's also such a thing as a column matrix, where you have only one column. If it's just got one column, you would call it a column matrix. Now, first, again, we're going to classify this by how many rows are there. Going from left to right, you got 2 rows by 1 column. So this would be a 2 by 1 matrix. Now, the biggest type we're going to work with in this course, and in really other subsequent courses to come, whether you take pre-calc or linear algebra or differential equations or stuff like that, you're going to work a lot with a square matrix. A square matrix is one where the number of rows and the number of columns are the same in each in the matrix. So if I look at this matrix 4, -1, 2, and 0, it has both 2 rows and it has 2 columns. So this is a 2 by 2 square matrix. If I look at this matrix here with 4, -1, 5, 2, 0, 1, 1, -3, and 6, I see I have 3 rows going from left to right. So this is a 3 by a 3 column. So this would be a 3 by 3 square matrix. And you could have a 4 by 4, a 10 by 10, what have you. That's so if a matrix has the same number of rows as it does columns, it's considered a square matrix. And then you have the 0 matrix where every entry in the matrix is 0, which we don't work with a whole heck of a lot, but it does come up periodically. A 0 matrix literally means it has zeros for every single entry. Let's classify this matrix. So How many rows are there going from left to right? 1, 2, 3. There would be 3 rows by how many columns? Going from top to bottom. 1, 2. This particular zero matrix is a 3 by 2 matrix. It has 3 rows and 2 columns. So in general, that's how you classify matrices and what matrices are. Now, we are going to talk a bit about matrix addition. So, and actually subtraction too. We'll talk about matrix addition / subtraction. So, matrix addition and subtraction. In order to add 2 matrices, so let's come up with a couple matrices here. In order to add matrices or subtract them, let me just write these. In order to add or subtract 2 matrices, both matrices must have the exact same dimensions. So here I have a 2 by 1 matrix, and then this is also a 2 by 1 matrix. Since they have the same dimensions, I can add. And what you should get another matrix that has the exact same dimensions as the 2 that you got there. So that's going to work. If I have a 2 by 1 plus a 2 by 1, I should also get a 2 by 1 matrix for my answer. And all I'm simply going to do is add the A and the C together. You add the corresponding entries, and then I would add B and D together. So you simply add the corresponding entries together in each matrix and you get your new matrix. And subtraction's the exact same way with matrices. They both have to have the exact same dimensions. So you would just subtract the corresponding entries. If I have a 2 by 1 subtracting a 2 by 1, my answer would also be a 2 by 1 matrix. I would take the A minus the C since they're corresponding entries, and then I would take B minus D. Those are for matrix addition and subtraction. So let's do some examples here. Let's start with these 2 matrices. We have 1, -4, -7, 2, plus another matrix of 3, 5, -5, and 2. First thing we have to ask ourselves is, can we even do this? Can we even do the addition? Well, what I would always suggest, until you get good at eyeing these up, figure out what the dimensions of each matrix are first. The first matrix here with 1, -4, -7, and 2, you have 2 rows and 2 columns. So this is a 2 by 2 matrix. The second matrix with 3, 5, -5, and 2, you have 2 rows and 2 columns. That's also a 2 by 2 matrix. So yes, since they're both the same dimensions, we can add these. We can totally do that. So to get your matrix, you're going to take the corresponding entries in each one and add them together. So my answer should also be a 2 by 2 matrix in the end. So I would add 1 and 3 together. So I'll take 1 plus 3. And then separately, I'll take negative 4 plus 5. And then I would take negative 7 minus 5. And then I would take 2 plus 2. So you see, you add the corresponding entries, and then that's going to turn into the 2 by 2 matrix 4, 1, negative 12, and 4. So yes, you can add these if they're both the same dimensions. You get the matrix 4, 1, negative 12, and 4. That's basic matrix addition at work. Now, what if we had something like this? We had 4, negative 2, 0, negative 6, that matrix, plus we have another matrix here with 4 and negative 1. Well, before we even try to do the addition, let's figure out what are the dimensions of each matrix. This first matrix here, it has 2 rows and 2 columns. This is a 2 by 2 matrix. What about the second matrix? Well, you still have 2 rows, but you have only 1 column. So these two dimensions are not the same. They are not the same for each one. It's not possible, because both matrices would need to have the same dimensions in order to be able to add them. Since they don't, you can't add these. It just doesn't work. All right. What if I took 7, negative 1, 4, 11, negative 9, 2. There's your first matrix, plus you would end up having the second matrix would be negative 3, 6, positive 3, 10, 1, and negative 5. So can we do the addition? That's a great question. Can we even do it? Well, let's classify these matrices first. It has, the first matrix has how many rows? It has 2 rows. Now how many columns does it have? 1, 2, 3. So the first matrix is a 2 by 3 matrix. What about the second one? You also have 2 rows, and then you happen to have 3 columns. Since both matrices have the same dimensions, we can totally do this. So we can totally do the addition, so that means your answer should also be a 2 by 3 matrix. So take your corresponding entries, add them together. Take your 7 and negative 3, add them together. That'd be 7 minus 3. Then take your negative 1 and 6 and add them together. Then take your 4 and 3 and add them together. Then take your 11 and 10 and add those together. Then take your negative 9 and 1 and add those together. And then take your 2 and negative 5, add those together, which would be 2 minus 5. Now you just do the simple addition and subtraction. You would end up getting the matrix 4, 5, 7, 21, negative 8, and negative 3. Which is also coincidentally a 2 by 3 matrix. So the resulting matrix will be 4, 5, 7, 21, negative 8, and negative 3 when you add these two together. All right. One more here of simple addition slash subtraction. What if we have this matrix? Actually, let's go down a little bit. This is going to be a bigger one. So we got 1, 6, -1, -6. And then we have 2 and 8 minus another matrix here of 7, -3, 9, -2, -7, 9, 11, -1, and 2. So we have these two matrices here. We're subtracting the second matrix from the first. So first thing, again, determine the order of each matrix. So of each matrix. So you definitely, in the first one, you have 3 rows, right? It's got 3 rows, but it only has 2 columns. So the first matrix is a 3 by 2. The second matrix, you still have 3 rows, but you have 3 columns. So since these two matrices do not have the same dimensions, this is not possible. We cannot do the subtraction because they don't have the same dimensions. All right, so that's basic addition slash subtraction. And if we could subtract, you would just subtract the corresponding entries and get your new matrix. Pretty much the same idea as addition. So, matrix addition. In general, when we talk about matrix addition, you would end up having, let's say you have matrix A plus matrix B. Well, you can take also matrix B plus matrix A. In that regard, matrix addition is commutative. And this is borrowing the fact, the idea that both of these matrices are able to be added. If they're able to be added, it does not matter what order you add them in. So matrix addition itself is commutative. Now let's say you had more than one matrix. So let's say I have matrix A plus matrix B in parentheses, plus a matrix C outside of that. Well, it would be no different than if I had matrix A on the outside this time plus matrix B plus C inside of parentheses. So matrix addition is also associative. So both matrix addition is both a commutative and associative because it wouldn't matter what order you move the parentheses for the associative, and it doesn't matter what order you add the two matrices for the commutative. You'll get the exact same result every time. Now, you can also multiply a matrix by what's called scalar multiplication. So let's talk about matrix scalar multiplication. Talk about what that is. So we're not talking about actual matrix multiplication yet. That'll be in the next lesson. That's a whole different topic. But let's say I had something like C, which is some arbitrary constant outside of the matrix RTU VWX. So I have a matrix here with entries RTU VWX. Outside I have some constant that I can multiply the matrix by. That constant C is called the scalar multiple. That would simply be, you're going to take that scalar multiple and multiply each entry of your matrix by that scalar multiple. That would give me a new matrix of C times R, which would be CR, C times T, which would be CT, C times U, which would be CU, C times V, which would be CV, C times W, which would be CW, and then C times X, which would be CX. That's all a scalar multiple does to a matrix. You just take that scalar on the outside of the matrix, multiply it by every term inside of the matrix, and then you have your new matrix. It doesn't change the order of your matrix, it just simply multiplies by a scalar multiple. So let's do a couple here where we're going to multiply a matrix by a scalar multiple. So let's say I give you -4 times the matrix with entries -1, -3, +7, -4, 0, and 6. So I have the matrix -1, -3, 7, -4, 0, and 6 times the scalar multiple of -4. So what am I going to do with that? Well, it's actually quite simple, really. I'm going to take each of my entries here and multiply them by -4. So if I do that, -4 times -1, that gives me +4. -4 times -3 gives me +12. -4 times +7 gives me -28. -4 times -4 gives me +16, actually. -4 times 0 gives me 0. And then -4 times +6 gives me -24. So, as you see, both matrices are still 2 by 3. They're the same order, but I've just simply multiplied each entry by a scalar multiple. Alright. Let's say I have 5 times -2, -6, 3, 1. So I have the matrix -2, -6, 3, 1 all being multiplied by the scalar multiple of 5. Well, this is a 2 by 2 matrix. My answer should still be a 2 by 2 matrix. The dimensions won't change. I'm just taking each of these entries and multiplying them by 5. So if I take 5 times -2, I would get -10. If I take 5 times -6, I would get -30. If I take 5 times 3, I'll get 15. And then if I take 5 times 1, I'll end up getting 5. So as you see, my new matrix is also a 2 by 2. I get the new matrix -10, -30, 15, and 5. Let's do one more for scalar multiplication, because scalar multiplication is actually pretty easy to understand. Let's say I take -9 times the matrix 0, 0, -2, -2, 1/3, and 4/9. Yes, you can actually have fractions and decimals and matrices. That is perfectly permitted. You can have fractions and decimals and matrices, yes, if you're wondering. Well, if it helps you, let's determine the order of the matrix. It's 3 rows, right, by 2 columns. This is a 3 by 2 matrix. So multiplying this matrix by the scalar multiple of -9 will not change the order of the matrix. So why don't we go ahead and do the multiplication? So if I multiply every entry by -9, -9 times 0 is still 0. -9 times 0 is 0. -9 times -2 is positive 18. -9 times -2 is also positive 18. -9 times 1/3 would be -3. -9 times 4/9 would end up being -4. So there's my new matrix. It's still a 3 by 2, but I get the new matrix of 0, 0, 18, 18, -3, and -4. Yeah, so that's scalar multiplication. Now, you can, of course, add and subtract matrices with different scalar multiples. So let's talk about distributive property. You can use the distributive properties of matrices also. So let's say I have a scalar multiple. I take that times matrices A plus B, right? Well, that's going to be the same as that scalar multiple times matrix A plus that scalar multiple times matrix B. And then I can still go ahead and add these two matrices together. So that's all that's saying, and likewise I can do it with matrix subtraction. If I do that, I take my scalar multiple times the quantity of matrix A minus matrix B. That would give me the scalar multiple times matrix A minus that scalar multiple times matrix B. So we've seen now that the distributive property works with scalar multiples and addition and subtraction with matrices. We've seen that matrix addition is both commutative and associative. Now, when we get to matrix multiplication in the next lesson, we're going to see that's not the case. It's different, but we'll cover that in that lesson, and we'll explain why it doesn't work then. But let's do a few problems here where we are going to add matrices plus scalar multiples. So let's say I give you something like, we got 12, -8. I probably better expand this actually a little bit. Then we have 0, 5, and then 0, 3, all that plus 4 times the matrix -1, 0, 3, -2, and then -4, 5. So we have one matrix plus another matrix times a scalar multiple. How are we going to approach that? Well, we can clearly see both of these matrices are 3 by 2, so we can definitely add them. Whenever you have scalar multiples, the PEMDAS rules apply. So you're going to do your scalar multiplication first on the matrices before you add. So why don't we go ahead and do that here? Let's do the scalar multiplication of the second matrix. So for now, keep your first matrix the same. This would be the same as your first matrix. Plus, now we're going to multiply this entire second matrix by that scalar multiple of 4. So if we do that, 4 times negative 1 is negative 4. 4 times 0 is still 0. 4 times 3 is 12. 4 times negative 2 is negative 8. 4 times negative 4 is negative 16. And then 4 times 5 is 20. So you see what I did there? I just took the second matrix, multiplied it by the scalar multiple of 4. Now I have this in a form I can work with. Always take care of your multiplication before you take care of the addition. So let's go ahead now and do the addition. So add the corresponding entries, 12 and negative 4, which would turn into 12 minus 4. Then you would take your negative 8 plus 0. Then you would take your 0 and 12. Then you would take your 5 and negative 8, which would turn into 5 minus 8. Then you would take your 0 and negative 16, which would turn into 0 minus 16. Then you would take your 3 plus 20. Which then will give you a new matrix, once you do the addition and subtraction, of 8, negative 8, 12, negative 3, negative 16, and 23. So notice you still get a 3 by 2 matrix, but we've done the scalar multiplication and the addition. You get the matrix 8, negative 8, 12, negative 3, negative 16, and 23. Let's do a couple more like this. Oh, good one. 2 times the matrix negative 6, negative 10, and 2 4, negative 7, and negative 4 minus negative 1, 5, 13, negative 3, negative 6, and 19. So here's your two matrices. You're taking the scalar multiple of 2 times your first matrix minus the second matrix. Well, once again, what you're going to want to do is take that scalar multiple times your first matrix here. So if we do that, multiply everything in the first matrix by 2, you would get 2 times negative 6, which is negative 12, 2 times negative 10, which is negative 20, 2 times 2, which is 4, 2 times 4, which is 8, 2 times negative 7, which is negative 14, 2 times negative 4, which is negative 8, all that minus your second matrices still, which would be negative 1, 5, 13, negative 3, negative 6, and 19. All right. So now, let's go ahead, do our matrix subtraction. These are still both, these are 2 by 3 matrices, so we can do the subtraction. So take your corresponding entries. You take negative 12 minus negative 1, which would turn into negative 12 plus 1. take your negative 20 minus 5, take your 4 minus your 13, then take your 8 minus your negative 3, which would turn into 8 plus 3, take your negative 14 minus negative 6, which would turn into negative 14 plus 6, then take your negative 8 minus your 19. So let's go ahead and work through that addition and subtraction in the matrix here. You'll end up getting the new matrix of negative 12 plus 1, that's negative 11. Negative 20 minus 5, that's negative 25. 4 minus 13 is negative 9. 8 plus 3 is 11. Negative 14 plus 6 is negative 8. Negative 8 minus 19 is negative 27. So after all is said and done, you get the new 2 by 3 matrix of negative 11, negative 25, negative 9, 11, negative 18, and negative 27. Now let's do one more with this. What if I had 3 times the matrix of negative 7, 1, 0, 8, negative 6, negative 2, minus 2 times the matrix 4, negative 1, negative 7. Then let's see, negative 3, negative 5, and 5. So this time both matrices have scalar multiples on them. You have 3 times the first matrix minus 2 times the second matrix here, okay? Again, first thing you want to do, take each of these matrices, do the scalar multiplication first. So let's go ahead and do just that here. If I take 3 times the entries of my first matrix, which, by the way, let's look at the order of each of these matrices. You have another 2 by 3 here and a 2 by 3 here. We can definitely do the subtraction. But let's do the multiplication for each of these matrices by the scalar multiple. If I take 3 times negative 7, I'll get negative 21. 3 times 1 is 3. 3 times 0 is 0. And then 3 times 8 is 24. 3 times negative 6 is negative 18. And then 3 times negative 2 is negative 6. Minus, let's just take 2 times our second matrix. So if I take 2 times 4, I get 8. 2 times negative 1 is negative 2. 2 times negative 7 is negative 14. 2 times negative 3 is negative 6. 2 times negative 5 is negative 10. And 2 times 5 is positive 10. Now we've done the scalar multiplication, and we have this in a form we can work with. So let's go ahead and do the matrix subtraction. And again, these are both 2 by 3 matrices, so we can totally do the subtraction. So you'll just subtract the corresponding entries and should get yourself another 2 by 3 matrix. So take negative 21 minus 8. Then take 3 minus negative 2, which would actually be 3 plus 2. Then take 0 minus negative 14, which would actually become 0 plus 14. Now take 24 minus negative 6, which would actually turn into 24 plus 6. Then take negative 18 minus negative 10, which would actually turn into negative 18 plus 10. Then take your negative 6 minus 10. And then we'll have our new matrix once we work through the addition and subtraction. So let's see, negative 21 minus 8 is negative 29. 3 plus 2 is 5. 0 plus 14 is 14. Then you have 24 plus 6, which is 30. You have negative 18 plus 10, which is going to be negative 8. Negative 6 minus 10 is negative 16. So your new 2 by 3 matrix that you should get as a result would be negative 29, 5, 14, 30, negative 8, and negative 16. Now, let's see here. I have 4 problems in which we are going to solve for some variables. So, let me demonstrate here what that's going to look like if you're ever given problems like these. So solve for x and y. Okay, so let's say you have negative 2x, negative 8, negative 10, negative 9 is equal to 6 y, negative 10, and negative 9. Well, okay, 2 matrices are truly equal if their corresponding entries are equal, if that makes sense. The corresponding entries of each matrix must be equal. And you see negative 10 in the first matrix equals negative 10 in the second matrix. Negative 9 equals negative 9 in the corresponding matrices in the corresponding positions. So the idea is with solving for x and y, we need to find those values that would make these 2 matrices equal. So this is actually quite simple. You're just going to take that negative 2x, set it equal to 6. Since the idea is that these 2 matrices are supposed to be equal, what do you get? You would get that x equals negative 3, right? Pretty simple. Then you see negative 8 corresponds to y. You would literally just set y equal to negative 8. And if you put these 2 values in for x and y, you would actually have 2 identical matrices. They would truly be equal. So I got 3 more problems like this. So it's really not that bad. Really not that bad at all. Now what if I had 3x, negative 2, negative 1, and 8, but that's not all. We're going to add another matrix to that, plus negative 4, 0, negative 7, negative 8, all that equal to the matrix of negative 16, negative 2, y, and 0. So the idea of these matrices here is that the sum of the first 2 matrices equals the matrix on the right. So we need to figure these out in such a way that we get a true statement. Well, on the left side you have matrix addition, which both of these are 2 by 2 matrices, and the one on the right side, the equal sign, is a 2 by 2 matrix. So this does check out. We can do the addition. So let's go ahead and do just that here. Let's add these 2 matrices in their corresponding positions. You would have 3x minus 4. Then you would have negative 2 plus 0. Then you would have negative 1 minus 7. Then you would have 8 minus 8. All that equal to the matrix on the right-hand side, which would be negative 16, negative 2, y, and 0. Which now, if we simplify this matrix on the left side, you get the matrix of 3x minus 4. Then you have negative 2 plus 0 is just negative 2. Negative 1 minus 7 is negative 8. Then 8 minus 8 is 0. All that should equal the matrix on the right-hand side. Again, that's the idea of solving for x and y in this case. What values will produce equal matrices? You see the 3x minus 4 corresponds to negative 16. So let's set the 3x minus 4 equal to negative 16, which would make 3x equal to negative 12, which would make x equal negative 4. So we found the value of x to be negative 4. Negative 2 equals negative 2, 0 equals 0, and then negative 8 corresponds to y. So y would just equal negative 8. So your value of x you should get is negative 4. Your value of y you should get is negative 8. And there's just 2 more problems like this, and then we're done for the day. So starting out with matrices really isn't that bad. They're actually kind of fun to play with. You have entered the matrix. All right. Now this time we have the scalar multiple on the outside of the matrix. We have 2x times the matrix of negative 3, 4, negative 11, and 5. All that equal to the matrix of 12, negative 16, y, and negative 20. So still the idea is that the left matrix ultimately will equal the right. But on the left side you have a scalar multiple of 2x. So why don't we go ahead and take care of that scalar multiple on the left, right? So let's do that. So if I go ahead and do that, take 2x times each of these entries, I would get negative 6x for the first entry. I would get 8x for the second entry. I would get negative 22x for this entry here. And then I would end up getting 10x for this entry. All that should be equal to the right-hand side of 12, negative 16, y, and negative 20. Well, here's a shortcut for you. Because you notice for the bottom left entry on each one, you would have negative 22x equals y. So you would actually have a 2-variable equation, but the shortcut is that every single entry, since you have a scalar multiple on the left, you'll get the same value of x for every entry. You'll get the exact same value of x. So you only need to figure this out once, what the value of x is. So go ahead and take any of these equations of x, set them equal to anything on the right. Let's say I take negative 6x, set that equal to 12, right? That would give me an x value of negative 2. And it checks out. And let me just demonstrate real quick. So negative 6 times negative 2 would equal 12. 8 times negative 2 would equal negative 16. And then 10 times negative 2 would equal negative 20. Now, we can solve for y by putting that negative 2 in at negative 22x. So y would equal negative 22 times that x value of negative 2. which means y would have to equal positive 44. So you should get an x value of negative 2 and a y value of 44 in the end. One more problem, then we're done. And this last one's going to be a bit bigger. We're going to have bigger matrices for this next one. Alright, so let's say I have 4, negative 3, 8, negative 7, 1 and 2. So I'm going to have 3 by 2 matrices this time, plus the matrix negative 5, x, negative 7, 7, 4, and negative 9 equal to the matrix of negative 1, negative 8, y, 0, 5, and negative 7. So still, the idea is the sum of the first two matrices on the left will equal the matrix on the right. We need to find the values of x and y that would make those matrices truly be equal. So on the left side we have matrix addition, and all three matrices are 3 by 2 matrices, so we can definitely do the addition. That's not going to be an issue. So let's go ahead and do just that on the left hand side. Take your corresponding entries and add them. So you'd have 4 plus negative 5, which would turn into 4 minus 5. Then you would have negative 3 plus x. Then you would have 8 minus 7, 8 plus negative 7 turn into 8 minus 7, negative 7 plus 7. Then you would have 1 plus 4. Then you would have 2 minus 9. All that equal to the matrix on the right, which would be negative 1, negative 8, y, 0, 5, negative 7. So let's simplify this matrix on the left. You'll end up getting, of course, negative 1. You'll still have x minus 3. Of course, the negative 3 plus x, since addition's commutative, it can turn into x minus 3, just to make our lives easier. 8 minus 7 is positive 1. Negative 7 plus 7 is 0. 1 plus 4 is 5. 2 minus 9 is negative 7. All that's going to be equal to the matrix on the left-hand side of negative 1, negative 8, y, 0, 5, and negative 7. Well, now we have it in a way we can solve. You see negative 1 equals negative 1 in the corresponding position. You see 0 equals 0 in the corresponding position. And both 5 and negative 7 are equal to each other in the corresponding position. So it looks like x minus 3 corresponds to negative 8. So we'll set x minus 3 equal to negative 8, which would give x a value of negative 5. So we found x to be negative 5, and it looks like y corresponds directly to 1. So y would equal 1. So you get an x value of negative 5 and a y value of positive 1. So that's it for the basics of matrices, what they are, adding, subtracting them, doing scalar multiplication with them, even doing variable equations with them to make them equal. The next lesson we'll get into matrix multiplication, which is different from normal multiplication. So I hope everyone has a great night. Take care.